So in this video I will be explaining the different types of stress. What is stress? So what is stress? Stress is simply the resistance offered by area. So when a load is applied, the member offer resistance to the load. Suppose we have a rigid body, a 5 kilonewton force is applied. The same and equivalent force but opposite, with magnitude same but of opposite sign, will be opposing that applied load. So the resistance offered will be the applied load. So when load is applied, the member offer resistance load which is the same magnitude but of opposite direction. So stress is simply resistance offered by area. Okay, that is the basic definition and equation of stress. A load when applied on the member will produce different types of stress. We can apply differently on a member. It could be axial load, torsion load. It varies on the type with which the load is applied, right? So based on that, there are different types of stress. The very first one is direct stress. So what is direct stress? Look at the given figure. It is having axially loaded member. The first one is in tension load because both the forces are applied away from the member, but on the second figure it is applied towards the member. So one is a tensile and the other one is compressive load. So at both A and B, the load here is represented as P, not F. So the P act along the axis of the bar, right? First one is tensile load and second one is compressive load. So these are called direct load, the one which is acting axially. Okay, it could be either tensile load or compressive load, but the load which is acting axially is known as tensile load. Okay, so these are direct tensile load or direct compressive load, varies on tension or compression. So what is it? Direct stress or direct tensile load or compressive load is simply P by A. What is P? The force applied by area. So in order to find direct stress or tensile stress or compressive stress, everything is same because it comes under direct stress. All we have to do is just divide the applied load by area. Next one is bending stress. So bending stress is formed by bending load. You are applying a load which causes the bending of the member. So in this figure we have given a cantilever beam. At one end we have now one end is hinged, right? That is a cantilever beam which will oppose the momentum at that point, a hinged point. It will not turn at that point. There will be a resistive momentum at the hinged point. On the other hand, the force P is acting downward. We know what happened. This force will cause the bending of that member, cantilever member. So if you imagine what really happened is when it bend on the top part, it will be having a tension and the bottom part will be having compression. Okay, that's how the distribution of stress in the member. The top part will be having a tension and bottom part will be having compression. So this is an explanation for finding bending stress in case of a bending load. So this is a definition. All I have to do is study the formula. We have consider load P acting on other end. So above and below the neutral axis passing through the center of the member. Okay, we know the top part will be having tensile and bottom will be compressive. So bending stress formula is simply sigma B is equal to mb by z. So mb is the moment. Okay, mb is the moment due to that bending force. The force P is acting downwards, it will cause a momentum, right? That momentum is eventually causing the bending of that member. So there will be a moment mb due to that force P. So mb by z. Z is section modulus. Section modulus varies with the different cross section based on the different structure. It could be circular, varies with the circular based on the geometry of the member. So z is equal to I by y. There's a formula for each member. I will show you later. Then so next is torsional stress. Suppose a body is having a momentum. We are giving a momentum or a torsional load. It will test, right? And eventually it will cause that torsional load will cause the will make a torsional stress due to twisting. So due to this, shear stress are developed in the shaft. For a torsional stress, we know shear stresses are the stress which is developed in the shaft. Okay, at an angle theta, there will be an shear stress due to the testing of the given torsional load. So in order to find that shear stress, tau is equal to mt into r1 by j. Mt is not simply momentum, it is applied torque. We'll be giving it definite torque in order to have that twisting momentum. So that torque, applied torque, is mt, and r1 is the any radius on the cross section of the shaft. It could be that distance we have to find. Okay, r1 simply, and j is the polar moment of inertia. Polar moment of inertia is also varies with the different geometric structure. So you have to learn for different structures. Okay, I will show that in table. So this is it for maximum. Okay, suppose we have a circular cross section. Suppose I have a circular cross section. So where do we get the maximum? Maximum distance possible is the very outer diameter, right? So I will be substituting that distance as d by 2. Then to find the maximum for a circular body, a cylindrical body, we know the cross section will be circular. Then tau max will be 16 into mt by pi d cube. So from that, the shear stress distribution for a torsional load we can find is very minimum at the center and maximum at the outer diameter. And this is a table for different structure. You can refer this table simply by adding the different values of moment of inertia and sectional modulus at a different point. So they are already they have mentioned it as the very outer distance, right, d by 2.